Thank you. It's a pleasure to be here. I am pleased to be at the College of Engineering here in Pune and to be part of the Honeywell initiative. I have a strong commitment to science and mathematics education, starting in the middle school and so forth. And in fact, I'm trying to start up a global set of teachers academies for training that. And one of the first academies is going to be in India, and I'm hoping another one will be here. But there's another reason I was glad to come to Pune. More than 2 decades ago, my father came to India, and he was an expert in hydrology, and he spent a lot of his time developing instrumentation and techniques for measuring water resources and so forth. And as an expert, he was brought in by the Indian government to set up monitoring stations and train people to eventually build what were irrigation projects. And then later he was brought in by the World Bank to decide which projects for the World Bank to provide loans for. And in fact, I know that one of the areas he worked was right near here. And I was flying in, I was trying to figure out which of those reservoirs or dams he might have personally been responsible for. So it's a closed family cycle. But my father taught me both the value of being a good engineer in technology and helping the world, as well as being an adventurer. Traveled all around the world in many ways. I have traveled all around the world, but now I want to travel around the universe with you. So we're going to talk about the history and fate of the universe, and I thought I would put it in context, but I wasn't able to find out if you actually have a program on TV here called CSI, which I was going to draw a parallel to, which in this case means the cosmic scene investigation. We're going to look around the universe and the room, see what we see, and try and reconstruct the events that started at the beginning of the universe and led to the present. And using the same sort of techniques that forensic science would use, find the clues, use your techniques, and discover what happened in the process. So we're looking for the relics of creation, and from those relics and like anthropology and archaeology, we're going to reconstruct what the early universe was like, and then use our models and propagate forward. So here's a picture of cosmologists at work, in case you don't have the program. You notice they carry notebooks and tools, and you can tell they're scientists because they have laptops with them, but they're crummy-looking laptops. And there's the techniques we use are evidence collection. We have a standard sets of tools and instruments that we use, which we depend very much on engineering. We have procedures that we've developed over time, and we do sophisticated computer analysis and simulations. Those are the very things that as engineers you're trained to do very carefully. So let me lead you through this. So one of our great instruments is the Hubble Space Telescope, and the Hubble Ultra Deep Field is this picture right here on either side. And in this picture, you can see, if you look carefully, that there are 4 stars. These things are stars. They're stars, you can tell, because the secondary of the Hubble Space Telescope is held up by 4 struts, and the diffraction around them gives a 4-fold symmetry. It could give 4 or 8-fold symmetry, but so forth. And so the stars are near point sources, so you get coherent reflection. You can tell them in a number of ways that those are stars. Everything else in this picture is a galaxy. Okay, so that should, impress you that you can't see the stars for the galaxies, right? It's like not being able to see the trees because of the forests. And you'll notice this galaxy right here. It looks very much like the galaxy we live in. And so when I look at this picture, the first question that comes to my mind is, are there intelligent beings in that galaxy trying to understand where the universe came from and so forth? And are there a few, besides the ones doing engineering, a few who are actually studying our galaxy trying to figure out what it is? But this is a relatively late galaxy. It's kind of yellow colored like the sun. It's a relatively nearby galaxy. So are these and these and these, right? But further off, you see smaller and more irregular galaxies. Those galaxies are further away, and they're younger in their development. And even so, we're not looking very far away. But in this picture, you can see a small number of thousand galaxies. What you have to know is the Hubble Space Telescope is just a tiny speck on the sky. If you were to get the Space Telescope working full time and survey the whole sky, you would have more than 100,000 times as much area as is collected here. So when you do the calculation, you find out there's more than 100 billion galaxies that you can observe with the Space Telescope. And that's roughly the same number of stars that we estimate exist in our own galaxy, except most of them are concentrated in a plane. But anywhere you look with the telescope where you can see a star, if you look behind it, you will see a galaxy. That tells you. So the first question you should ask yourself as an engineer, if I was given the job of making the universe like this, how could I do it on time and on budget, right? Because that's part of the deal. You know, if I was just making a universe so that there could be human life, I could get by with a solar system probably, but one galaxy would be enough. Why would I make 100 billion, right? I mean, okay, and why does it cost me so much? So that's the mystery that we have today. When I was young and started out, we didn't have beautiful pictures like this. We had a few pictures of individual galaxies, and you had to imagine what the sky would look like. But that's the story. So I'll start the story. The story of science is about 400 years old, but this is a story that starts about 100 years ago with Albert Einstein. And you will notice that he got chosen by Time magazine to be the person of the century. And the question is, which one of you guys is going to be the person of this century? And we'll see. So the thing that he gave us was this a change in our view of gravity, and that change in the view of gravity leads to the idea of the expansion of space. So Einstein published the general theory of relativity in 1915, and in that he implied that space-time is curved whenever you put matter and energy into otherwise empty space. It causes space to curve, and the curvature of space then back reacts on the matter and energy and tells it how to move around in that space. So there's a symmetry there. But if you have a curvature of space, you also have a scale to space. So if you say space is curved, say curved like this, there's a certain radius of curvature, that is a tangent sphere you could put to it, that gives you a scale. And that scale can change with time as a thing. And so it turns out that solutions were derived by various people. The first two people to do a serious solution were Georges Lemaitre, who was an abbé in the Catholic Church in Belgium, and he wrote a thing called the hypothesis of the primeval atom, roughly translating the French. And the other person was a meteorologist in Russia whose mathematics was very good. It's Alexander Friedman. And both of them found solutions to the universe that involved an expanding universe. Friedman also found solutions that involved a contracting universe. And this was not something that made Einstein very happy. And in a minute we'll talk about de Sitter, who came up with a solution that even made Einstein more unhappy. And so here's a picture roughly from that time of Albert Einstein and Lemaitre at the time of this. And Einstein, when Lemaitre mailed him his paper, wrote back, "Your mathematics is correct, but your physical intuition is an abomination," because everyone in the world knew the universe is static. In fact, we've known it for a long time. The Greek word planet means wanderer, that is, the things that move in the sky. Everything else was a fixed star, right? So everyone has known, had knew up to 100 years ago, essentially for 2,000 years or more, that the sky was unchanging. And Einstein knew it so well that he couldn't believe that the universe would be expanding. And he actually went back and modified the equations of general relativity, adding the cosmological constant to try and find a static universe. That turned out to be, he says, his greatest blunder. He said that was his greatest blunder. But it also turns out to be unstable, a situation that actually Newton, when he tried to make cosmology, realized that if you try and make an infinite universe, it's unstable against collapse or expansion. And so this situation was such that it forced Einstein to modify his equations of general relativity from their simplest possible form to the next simplest possible form. And here's a picture of Einstein, Lemaitre, and Millikan, who measured the charge on the electron. It's the only American in this picture. Wilhelm de Sitter and Friedman, because Wilhelm de Sitter used the cosmological constant to create a universe that had no matter and energy in it, just the cosmological constant, and that's also something that Einstein really hated. This is Alexander Friedman, a meteorologist. Wasn't really recognized his work until later. This was after the time that I'm going to tell you about next, after the discovery by that the universe really was expanding. So here's the idea that comes from general relativity. So imagine that we suppress one of the three spatial dimensions so that we think of the universe as being the surface of a balloon, and you put nice grid lines on it, and you let that balloon expand with time, and you'll notice the grid lines expand along with the balloon. That's the scale changing of what's going on. But it's a convenient coordinate system that allows you to keep track of things. If you nested the balloons inside of each other, your constant angles out on the sky. And you'll notice the galaxies, and if you watch, say, this galaxy, it's right on the cross It's right on the cross, that locally that galaxy does not move.